Jimmy Akin's Mysterious World is brought to you by the Star Quest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit sqpn.com/give. You're listening to episode 372 of Jimmy Akin's Mysterious World, where we look at mysteries from the twin perspectives of faith and reason. In this episode, we're talking about the Drake equation and the search for extraterrestrial intelligence. I'm Dom Bettinelli, and joining me today is Jimmy Akin. Hey, Jimmy.
Howdy, Dom.
Folks, be sure to stick around to the end of the episode as we'll have your feedback on our recent episode on the mystery of the year. But first, for decades, scientists have tried detecting intelligent life beyond the Earth. This is known as the search for extraterrestrial intelligence. And one common way of doing it is by using radio telescopes to look for radio transmissions from other solar systems. But all such efforts presuppose that there's someone out there we could talk to. And that raises the question of just how many alien civilizations there are. In 1961, astrophysicist Frank Drake tried to estimate how many there might be, so he came up with a mathematical formula now known as the Drake equation. So what is the Drake equation? How have estimates changed over the years, and how many alien civilizations are actually out there? That's what we'll be talking about on this episode of Jimmy Akin's Mysterious World. Jimmy, what would you like to say to begin?
Well, today's episode is one in a series of episodes that look at the idea of extraterrestrial life from a scientific perspective. The original installment in this series was way back in episode 10 on the Fermi paradox, which deals with the question of why we allegedly don't see evidence of extraterrestrial intelligence. Of course, some people would say that we do. I mean, what do you think UFOs are, they say. But other people dismiss these claims. In the future, we'll also have an episode looking at the search for extraterrestrial intelligence, or SETI itself. But today, we're looking at the related question of whether we can figure out how many civilizations there are that we might be able to detect. And that brings us to the Drake equation, which has been said to be the second most famous equation in science, yielding first place, of course, to Einstein's E=mc².
Then let's look at who the creator of the equation, Frank Drake, was. What can you tell us about him?
Frank Drake was an American astrophysicist and astrobiologist after astrobiology became a thing. He was born in Chicago, Illinois in 1930. He studied at Cornell and Harvard, and he taught at places like Cornell and the University of California at Santa Cruz. He also worked at places like the Jet Propulsion Laboratory and the SETI Institute. He originally was a radio astronomer, and he discovered things like the planet Jupiter has a magnetic field. By 1959, he was wondering if we might be able to detect radio transmissions from alien civilizations, and he got approval to start an effort named Project Ozma to look for them. Project Ozma was named after Princess Ozma, a ruler of the land of Oz from Frank Baum's books about Oz. The name was inspired by the fact that Baum playfully claimed that he had begun receiving radio transmissions from the land of Oz, which let him write many of his later Oz books. Originally, Drake kept Project Ozma a secret, since people might think they were crazy, but later in 1959, two physicists published an article in the journal Nature about searching for interstellar communication, and so Drake decided to publicize the project. The project began in 1960, and it used a radio telescope in West Virginia to study the nearby stars of Tau Ceti and Epsilon Eridani, but they didn't find anything. Around this time, Drake was contacted by astronomer Carl Sagan, who was just a grad student at the time, and they became regular partners in scientific endeavors. In 1961, Drake came up with the Drake equation, which we'll have more to say about in a bit. In 1972, Drake helped design the Pioneer plaque, which was a pictorial message that was attached to the space probes Pioneer 10 and Pioneer 11, just in case aliens ever found them. In 1974, Drake wrote the Arecibo message, which was the first human message deliberately broadcast from Earth for aliens to listen to. It was transmitted from the Arecibo radio telescope in Arecibo, Puerto Rico, towards the globular cluster Messier 13. And it was a notable achievement, though it's really primitive by today's standards. If you ever see it, and we'll have an image of it in the video version of the podcast, it looks like something out of an early super low-res video game, though there are scientific principles encoded in it, so the aliens could recognize it as a sign of intelligent life, or at least a sign of a species that has begun designing crappy video games.
And over here is our crowning achievement in amusement technology. An electronic version of what you call table tennis. Your primitive paddles have been replaced by an electronic...
Hey, that's just Pong. Get with the times, man.
Marge and I played that old game before we were married.
Well, we did build this spaceship, you know.
Anyone from a species that has mastered intergalactic travel, raise your hand.
In 1978, Drake helped oversee the development of the Voyager Golden Record, which was on board the Voyager 1 and the Voyager 2 space probes, and which should provide the aliens with some Earth tunes to chill out by when they play Pong. Because, among other things, we sent them Bach's Brandenburg Concerto No. 2, and we sent them Chuck Berry's Johnny Be Good.
Deep down in Louisiana, close to New Orleans, way back up in the woods among the evergreens, there stood a log cabin made of earth and wood, where lived a country boy named Johnny Be Good, who never ever learned to read or write so well, but he could play a guitar just like a ringing a bell. Go, go!
So Drake retired from teaching in 1996, and he passed on to his reward in 2022 at the age of 92.
With that as background on the man who came up with the formula, let's talk about the Drake equation itself. How did Frank Drake come up with it?
Well, in 2003, Drake gave a talk in which he discussed this, so I'll let him explain.
This all began shortly after I conducted the first search for extraterrestrial intelligent radio signals at the National Radio Astronomy Observatory in Green Bank, West Virginia. That was in 1960. At that very same time, a very seminal paper was published by Philip Morrison and Giuseppe Cocconi, pointing out what I had already realized. And that was that we had the ability to detect reasonable signs of intelligent technology across the distances which separated the stars. This in one way opened the door to detecting life, in this case specifically intelligent life, beyond Earth. A great new window of possibilities was opened, which was slowly recognized at the time, and of course is widely recognized today. It's expressed by the great growth in the field of astrobiology. Shortly after this, the National Academy of Sciences wanted to convene a small meeting to examine this whole question and propose where we should go from here. They asked me to do this, and indeed, just about 42 years ago at this time, I sponsored the first such meeting at Green Bank. I was the entire scientific and local organizing committee, but it wasn't a hard task because I invited every person in the world we knew of who was interested in working in this subject. All 12 of them. And all 12 of them showed up. As I planned the meeting, I realized a few days ahead of time we needed an agenda. And so I wrote down all the things you needed to know to predict how hard it's going to be to detect extraterrestrial life. And looking at them, it became pretty evident that if you multiplied all these together, you got a number, n, which is the number of detectable civilizations in our galaxy. This, of course, was aimed at the radio search, and not to search for primordial or primitive life forms.
So Drake said that he basically came up with the formula on a few days' notice. He was planning a very small conference in Green Bank, West Virginia, which was where the telescope that they were using for Project Ozma was. And the formula basically emerged out of a list of the things that we need to know to predict how hard it would be to detect alien life. He realized that if you knew all those factors, you could multiply them together and get the number of civilizations that we might discover.
Then let's talk about the formula itself. What did Drake come up with?
Well, here we come to a bit of a difficulty for a podcast, whether audio or video, because the formula uses values that will be hard to keep track of in audio or video form. Properly speaking, the formula is N equals R sub star times F sub P times N sub E times F sub L times F sub I times F sub C times L. But that's a real mouthful and would be too confusing, so we won't be using all that jargon. Instead, I'll give the factors in the equation easier to figure out names. The first factor in the equation, the one that we're really interested in, is the number of civilizations that we can communicate with. To get the number, you multiply together a series of factors. The first of these is the average rate at which stars form in the galaxy. That is, how many new stars form every year. The next factor is the fraction of stars that have planets. The next is the average number of planets which such stars have that are habitable. The next is the fraction of habitable planets that develop life. Then comes the fraction of planets with life that develop intelligence. Then the fraction of intelligent life forms that develop technology. And finally, there is the average lifespan of these civilizations in terms of how long they communicate, or really how long they remain detectable, as we'll see later. So if you put all that together, the number of civilizations we could discover should be stars times planets times habitability times life times intelligence times technology times lifespan. And taking those factors in reverse order, you can see why each is needed. We obviously have to be within the period in which a civilization is communicating with their technology if we're going to detect them. If they're not yet communicating, or if they've stopped communicating, that doesn't do us any good. So the longer their lifespan of communication is, the better. But that presupposes that they've developed technology, which initially was assumed to be radio communications technology. And if they've developed technology, well, then they have to have intelligence. But to have intelligence, they first have to be alive, so they have to have life, which means that they're on a planet that must be habitable. And that means that their star has planets in the first place, and the planets need to be orbiting one of the stars in our galaxy. So the more stars, the better the chance of finding someone, and thus the rate of star formation becomes important because stars have life cycles, and even if a star has habitable planets at one point, it won't have them forever, like when the star swells and then collapses into a white dwarf, or when it explodes and becomes a neutron star or even a black hole. So they use the rate of star formation instead of the total number of stars in this version of the equation. And if you can determine all those numerical values and multiply them together, you get the number of civilizations in our galaxy that we might discover. And if we wanted to, we might even beam a message to them and start an interstellar conversation.
Okay, so those are the factors that are involved in the Drake equation. What happened when the scientists met back in 1961? What numerical values did they plug into the equation?
Well, based on the science of the time, they estimated that the stars form in the Milky Way at the rate of 1 per year, although they were really focused on sun-like stars, and that'll change a bit when we get to newer estimates. They weren't sure how many stars had planets back then, since we couldn't yet detect exoplanets, so they estimated that 1 in 5 to 1/2, or 20% to 50% of stars had planets. For those stars that had planets, they estimated that these solar systems would have between 1 and 5 planets that are habitable, and we'll have more to say about that estimate a bit later on. When it comes to the chance that a habitable planet would actually develop life, so not just that it was habitable and that could have life, but that it actually developed life, they were much less sure about this because we only have our own solar system to look at. But they estimated that the odds are 100%. In other words, if a planet is habitable, then it will develop life eventually. Then, if a planet develops life, what are the odds that it will come to host intelligent life? Here again, based on the data that we have only from looking at Earth, they guessed that it would be 100%. However, they were more conservative when it came to whether intelligent life would develop the ability to communicate through technology like radio. Here, they estimated that only 10 to 20% of intelligent species would develop such technology. And finally, they guessed that the communications lifespan of such civilizations would be somewhere between 1,000 years and 100 million years.
So, what do you get when you combine all those numbers? How many species might there be in the Milky Way that we could discover by their radio signals?
Well, you'll note that some of these factors have ranges, so you get different answers depending on whether you pick the minimum values in the ranges or the maximum values in the ranges or somewhere in between. If we do a lowball estimate and use the minimum ranges throughout, then it turns out that there would be only 20 detectable civilizations out there in the Milky Way. On the other hand, if you use the maximum values, then there would be 50 million detectable civilizations out there. So based on the numbers they used back in 1961, there should be between 20 and 50 million detectable civilizations in our galaxy. Or if you split the difference between those numbers, about 25 million. Of course, those estimates are based on the numbers they had available back in 1961, which was 64 years ago, and we have new and better estimates for some now.
So before we move on to the analysis of the Drake equation, we'd like to first take a moment to thank our patrons who make this show possible, including Alvin W., Christian E., Katie K., Andrew W., and Simon M. Their generous donations at sqpn.com/give make it possible for us to continue Jimmy Akin's Mysterious World and all the shows at StarQuest, and you can join them by visiting sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you by DeliverContacts.com, offering top brand contact lenses at always low prices with free delivery. Visit DeliverContacts.com. And by The Grady Group, a Catholic company bringing financial clarity to their clients across the United States, using safe money options to produce reasonable rates of return for their clients. Learn more at GradyGroupInc.com. Now, Jimmy, before we get to the reason perspective, what can we say about the Drake equation from the faith perspective? Is there any fundamental conflict between it and the Christian faith?
Well, in principle, no. The Bible and the church don't have anything to say about whether God chose to create intelligent life elsewhere in the physical universe. If he did, they would just be other children of God. So there's no fundamental conflict with the idea of there being intelligent creatures elsewhere in the physical universe. Or with the idea that some of them might be using technology the way we do, or that we might be able to detect this technology. Incidentally, we talked about the theological implications of the discovery of intelligent life elsewhere back in episode 55 on aliens and religion. So you can go back and listen to that for all the theological questions you might be wondering about, like whether aliens would need a savior or whether they'd be saved through Jesus Christ. But beyond this, the issue of the Drake equation itself requires a bit more discussion. The Christian faith teaches that God is ultimately in control of all reality. It's he who set it up, and it's he who determined the rules it works by. However, Christian thinkers have long recognized that God doesn't do everything by himself. He uses what are known as secondary causes to achieve his ends. For example, God's will is that babies get the milk they need, but he doesn't materialize this milk in their mouths. Instead, he allows their mothers to serve as secondary causes so that they participate in God's plan by feeding their own children. In the case of humans, he also gives his secondary causes, or us, free will. And it's hypothetically possible that a human mother could misuse her free will and deny her child food, though as with any evil, God would only allow this if he was going to bring about a greater good. God also uses secondary causes in nature. For example, the device that you're listening to this podcast on is electronic in nature, so it depends on electrons flowing through its circuits. According to the standard understanding, it is not God himself who pushes these electrons through the circuits. Instead, he created a natural law of electromagnetism that causes the electrons to flow in a certain way. A difference between this type of secondary cause and the human ones is that electrons don't have free will, so they're not moral agents and they always do what they're supposed to. They're like tiny robots. But then, sometimes God doesn't use secondary causes. Sometimes he intervenes directly, like when Jesus rose from the dead, despite the fact that this departs from the normal course of nature. This maps onto some of the issues, this schema maps onto some of the issues that are involved in debates over origins, like how did the universe, life, and mankind emerge? It's universally agreed among Orthodox Christian thinkers that God created the universe out of nothing. And since nothing else existed, that had to be a direct intervention on God's part, since he didn't use anything else as a secondary cause in the original creation of the world, because there was nothing else to use as a secondary cause. Whether you identify the moment of that creation with the Big Bang or with something else, this would still be true. But then, once the universe was created, it had secondary causes in the form of natural laws working in it. And these laws led to certain things happening, like gravity, causing stars and planets to form on the standard understanding. Gravity was thus functioning as a secondary cause to bring about God's plans. The question is, how much was left to secondary causes, and how much did God choose to do by direct intervention? Some people think that there are certain moments in the history of life that require divine intervention. In other words, they are moments that the natural laws God set up cannot produce. One of these moments is the emergence of life from non-living matter. Another is the emergence of one species from another, and a third is the emergence of intelligence. But two of those, the emergence of life itself and the emergence of intelligence, are factors in the Drake equation. So what you think about this theological matter has an impact on the Drake equation.
Does that make the Drake equation useless?
Well, it may or may not from a scientific perspective. In the first place, the idea that life can't emerge from non-living matter and so forth is just an opinion. It's not a teaching of the church. So it's possible that God could use secondary causes to produce life, to allow species to change, and to bring about intelligence. And if he does allow secondary causes to do these things, then we should be able to predict them in principle, and the Drake equation will work just fine. On the other hand, he may not have set up the natural laws in the world to do these things. One or more of these things may require divine intervention, in which case the question turns into how predictable God chose to make these interventions.
What do you mean? Aren't divine interventions unpredictable by their very nature?
No, I don't think that's necessarily true. The things that we can identify as miracles, like Jesus rising from the dead in a glorified form, those can't be predicted in advance, unless, of course, God tells you he's going to do it. The reason is that things like this depart from the ordinary course of nature in a dramatic way, and that gives you reason to hold that something beyond nature, something supernatural, was responsible for the event, so we call it a miracle. If we can identify something as a miracle, then yes, it's unpredictable. But just because God is intervening in the world doesn't mean that he tells us that he's intervening. You'll recall that I said, according to the standard understanding, God created the universe and then gravity kicked in and caused stars and planets to form. But we don't really know what gravity is. It's possible that there is no such thing as gravity and that God intervenes to use his own power to accomplish everything that we attribute to gravity. If so, then there are divine interventions taking place constantly. It's just that we can't identify them as miracles because they occur so regularly. Thus, when we see someone throw a stone and it falls back to earth, and we see this happen so regularly that we can describe the stone's fall mathematically, we assume that there is a force that we've named gravity causing this to happen, but it really could be divine intervention that's just so regular it looks like a natural law to us.
Then how does this affect the Drake equation?
Well, suppose that the emergence of life and the emergence of intelligence do require divine intervention. But suppose that God chooses to intervene to bring these things about in a regular way. But suppose that among the habitable planets, God decides to create life on 1 in 4 of them. And suppose that among the planets with life, God decides to create intelligent life on 1 in 5 of them. Well, then you can just plug the factors 1 in 4 and 1 in 5 into the Drake equation and it works. If he does these things consistently when certain conditions are fulfilled, then we can predict for which planets it will happen. And we won't be able to distinguish it from a natural law. We'll just describe that law as saying that when you have this combination of factors, you get life. And when you have this other combination of factors, you get intelligence, even though it's really all divine intervention. On the other hand, God might not choose to do this in a fully regular, predictable way. Maybe he picks which planets will get life randomly and which planets will, with life, get intelligence randomly. In that case, we can't specify a natural law, but with enough data, we could still specify a probability. For example, if we're someday able to do a big survey of the atmospheres of exoplanets and we find that 1 in 4 of the habitable ones have biomarkers indicating the presence of life, then we know that we need to plug 1 in 4 into the life factor of the Drake equation. And if we do a survey of planets with life and find that 1 in 5 have technosignatures indicating life with technology, then we know 1 in 5 needs to be plugged into the equation there, even if there's no pattern to which specific planets get life or technology. It's just God's random choice. Either way, the Drake equation still works, so it doesn't matter whether God lets secondary causes like natural laws bring about life and intelligence, or whether he does it himself in a regular way, or whether he does it himself in an unpredictable way. The Drake equation will still work if we can get enough data. So the faith perspective doesn't have a problem with it. However, at this point, we're going to turn to the reason perspective, and from that perspective, we'll be assuming that God doesn't do things completely unpredictably. In other words, that God either lets secondary causes bring about life and intelligence, or that he does it himself in a way that's regular and predictable. Now, this is just a heuristic assumption, meaning that it's something that we assume tentatively for practical reasons to see how far this line of reasoning will let us go, but it's not something that we could know without a lot more data.
Then what can we say about the Drake equation from the reason perspective? Before the break, we saw that the 1961 values plugged into the equation could imply as few as 20 detectable civilizations in the Milky Way and as many as 50 million. That's a really wide range. It's a 6 whole orders of magnitude. If there's that wide a range of answers, does the Drake equation really have any scientific value?
Well, given the present uncertainty about the values that need to be plugged into the equation, we're not going to be able to use it to make specific predictions, like figuring out how close the nearest such civilization is. I mean, you can try to do that, but the uncertainty, or what in science are sometimes called the error bars, are just too big for any such calculations to be realistic. However, this doesn't mean that the exercise lacks scientific value. Originally, the equation itself was kind of an afterthought. Frank Drake first came up with the list of factors on the fly while he was planning a conference agenda, and then he realized, oh, you could turn this into an equation. So the real value was figuring out what kinds of things we needed to research to get into a position where we could make reliable predictions. The effort thus has value as an intellectual guide to the overall issue and as a guide for further research. It helps tell us what kinds of things we need to study, like, for example, how easy or hard it is for life to appear on a planet, or how easy or hard it is for intelligent life to arise, and so forth. And this is true regardless of whether you think intelligent aliens are out there to be detected or not, because people fall into different camps on that. Some scientists emphasize what's known as the principle of mediocrity, which is the idea that Earth is not a super special place, and so places with intelligent life like Earth ought to be common. On the other hand, some scientists think that Earth is a super special place, and that intelligent life should be very rare or even non-existent elsewhere in the galaxy. They hold what is known as the rare Earth hypothesis, since places like Earth are supposed to be rare on their view. But it doesn't matter whether you're a mediocritarian or a rare earther. Mediocritarians can use the Drake equation to argue that detectable intelligence should be common, and rare earthers can use the Drake equation to argue that detectable intelligence should be rare. The Drake equation's real value is that it lets us identify and organize the relevant variables to discuss and argue about what they are and guide research into figuring out the answers. It's thus not an equation that will let us make easy predictions because we don't yet have the data we need, but it is a useful guide to help us think through the problem.
Then let's look at what scientists have learned in the last 64 years. We know a lot more about astronomy now than we did back then. So what progress has been made in figuring out the variables in the Drake equation? Let's start with the rate of star formation. What have we learned about that?
Well, there's good news here for fans of alien life in that current studies for the rate of star formation in the Milky Way have gone up. In 1961, they estimated that the value for this was 1 star per year. Back then, they were focused on estimating the number of sun-like stars that were forming because they assumed that only such stars would have habitable planets. But we now know that other stars can have habitable planets too, and so today we aren't focused on just sun-like stars. More recent estimates have put the rate at something like 7 stars per year in the galaxy, and it may even be higher than that, according to research published in 2023. Science News states,
"The Milky Way is churning out far more stars than previously thought, according to a new estimate of its star formation rate. Gamma rays from aluminum-26, a radioactive isotope that arises primarily from massive stars, reveal that the Milky Way converts 4 to 8 solar masses of interstellar gas and dust into new stars each year," researchers report in work submitted to archive.org on January 24th. That range is 2 to 4 times the conventional estimate and corresponds to an annual birth rate in our galaxy of about 10 to 20 stars, because most stars are less massive than the Sun.
So if these recent findings are accurate, that would put the rate at around 10 to 20 stars, which we can average to 15 stars per year, and that's 15 times better for the prospects of detecting civilizations.
If that's what happened with the star formation rate, what about the chances of those stars having planets? We have found thousands of exoplanets in other solar systems, none of which were known in 1961. What's that done to the second variable in the Drake equation?
Well, it's also gone up. Back in 1961, they thought that somewhere between 1 in 5 and 1 in 2 stars might have planets, or 20 to 50%. The rest were just lone stars with no planets. But based on more recent astronomy, it looks like that's not the case. Instead, stars having planets seems to be the norm. And so these days, a common estimate is that every star has at least one planet. That planetary formation is just a byproduct of star formation. And so a modern estimate would increase the planet factor to 100%.
What about the number of habitable planets that this typical star has? Have our exoplanet discoveries shed any light on that?
Some, but the matter has gotten more complex. Back in 1961, they estimated that the average star with planets would have between 1 in 5 habitable planets. And that might sound like a lot because we tend to think of Earth as the only habitable planet in our solar system. But actually, we have 3 habitable planets in the habitable zone around our sun. Those planets are Venus, Earth, and Mars. Venus may have had a liquid ocean and have been habitable for billions of years before it developed a runaway greenhouse effect. Mars also had a liquid ocean before it lost most of its atmosphere, but it was also habitable for a long time. And there's a very good chance that life is still there today, as we discussed back in episodes 179 and 180 on Life on Mars. So despite the fact that only Earth is easily habitable for humans today, our solar system actually has at least 3 places that have the potential to harbor life. And so an estimate of 1 to 5 planets being habitable in a system with planets is not unreasonable. When it comes to more recent estimates, the matter is complicated by the fact that we've realized that there may be habitable environments outside the habitable zone around our sun. We sometimes call this zone the Goldilocks zone because of the amount of heat coming off the sun is just right to allow liquid water on the surface of the planet. You know, it's not too hot for liquid water to exist. It's not too cold for liquid water to exist. So the temperature is just right to allow life. But water doesn't need to be on the surface for life to exist. If there's liquid water below the surface, like in a subsurface ocean, then life could exist there too. Also, the sun is not the only source of heat. Heat can also come from pressure being put on ice by geological forces, including the gravity of large nearby planets. Thus, some of the moons of Jupiter and Saturn appear to have subsurface oceans of liquid water, among some other bodies that are outside of the habitable zone generated around the sun. So if we look at bodies that today or used to have liquid water oceans, we not only get Venus, Earth, and Mars, we also get Jupiter's moons Europa and Ganymede, and Saturn's moons Enceladus and Mimas, as well as the planet Ceres in the asteroid belt, and even the planet Pluto may have had a water ocean in the past. And these are only the places where we've discovered evidence of water oceans. There may be additional bodies in the solar system, like additional moons of Jupiter and Saturn, that also have them. But sticking with just the bodies where we currently have evidence for a water ocean existing or haven't existed, we would jump from 3 habitable places in our solar system to 9. Remembering, of course, that round moons are actually planets, since if something is big enough to be round but not big enough to glow, we need to classify it as a planet, and that includes Pluto too, no matter what the International Astronomical Union foolishly says at present. But regardless of terminology, we currently have evidence for 9 habitable locations in our solar system. On the other hand, we now have evidence from our studies of other solar systems that the structure of our system is likely unusual. Lots of solar systems have Jupiter-sized planets close in to their stars, making them what are called hot Jupiters. It's possible that such Jupiter-like planets form in the outer solar system and then migrate towards their star, in which case they might disrupt the orbits of smaller planets in the habitable zone and, for example, eject them from the star system, resulting in most solar systems having fewer habitable planets than ours. But the fact that we've got moons that can have liquid water oceans means that we can't just look at the planets. And so even if most systems have fewer planets in the habitable zone, they may have just as many habitable moons. Also, if you think about it, we don't actually need an entire planet to be habitable to have life. For example, there are some planets that are locked to their stars by tidal forces, so that one face of the planet always faces the star and gets really hot, while the other side of the planet always faces away from the star and gets really cold. Well, in between these two sides of a tidally locked planet is a zone that is neither hot nor cold, and that zone on the planet could be habitable. So if you just look at the temperature or the presence of liquid water to determine habitability, the average number of habitable places in the solar system might be quite high. But rare earthers want to knock that number down, and they propose that additional factors are needed for habitability, like not being too close to the galactic core so that radiation from the core doesn't sterilize the system. And by the way, we may devote a future episode to the rare earth hypothesis and see how likely it is compared to the mediocrity principle. However, at present, from what I've been able to find out, it doesn't appear to me that there is agreement on what value or range of values should be plugged into the habitable factor in the Drake equation. So without an updated consensus, I'm going to leave this one as it was and assume a range of 1 to 5 habitable places in a typical solar system, even though it could be substantially higher or lower than that.
Okay, then what about the chances that a habitable planet will come to have life on it? What do current estimates say about that?
Back in 1961, they estimated a 100% chance of a habitable planet coming to have life. And this is a bit of a placeholder because the actual value would almost certainly not be exactly 100%. I mean, if there were even one habitable planet in the universe that didn't get life, it wouldn't be 100%. But they estimated that the fraction was so close to 100% that it didn't really make a difference. However, this was a guess, and the question is whether it was a good guess. One way of looking at the problem would be to regard Earth as the only habitable place in our solar system, and, well, since life is here, that's a 100% chance of life in a habitable place. But there are 2 problems with this way of looking at things. The first is that this approach involves what can be called anthropic bias. Anthropic means connected with man. And so anthropic bias means that just looking at the Earth biases the question because there has to be life here because man is here. If humans didn't exist on this world, then we wouldn't be here to notice whether or not there was life. So the fact that we are here to notice the life means our planet must have life because of us. The second problem is that Earth is just not the only habitable place in our solar system. I've seen it argued that our system has 2 habitable planets, Earth and Mars, and life developed on one of those 2 worlds, the Earth, so the actual percentage here should not be 100%, but 50%. Except that this is problematic because we don't know that life never arose on Mars. As we saw in episodes 179 and 180, it looks like life may very well have arisen on Mars, and even that it's still there. So that would return our estimate back to 100% if you consider just those 2 habitable places. But there are more habitable places in the solar system than just Earth and Mars, because we actually have indications of life on Venus. First, there's something unknown in Venus's atmosphere that absorbs ultraviolet or UV light. And Carl Sagan proposed back in 1963 that this unknown UV absorber could be microorganisms in the Venusian atmosphere that are feeding off the UV light emitted by the sun. And second, in 2020, the compound phosphine was detected in the Venusian atmosphere. This was disputed, but it was confirmed in 2024. And on Earth, phosphine is associated with anaerobic organisms, or organisms that don't require oxygen. Further, phosphine should not be present in the Venusian atmosphere because of the UV radiation that would break it down. So something seems to be renewing the phosphine. And so we have at least a couple of lines of evidence suggesting life on Venus. This life may have begun billions of years ago, back when Venus was more habitable and had a water ocean, and then once its runaway greenhouse effect kicked in, some of this life managed to adapt and survive in the atmosphere. So we have potential evidence for life on all 3 of the 3 major planets that might have life on them. But we don't know that Venus and Mars have life. They might not. Then there are the moons and such that have habitable locations, and we have no idea whether they have life or not. So until we've fully explored our own solar system and had a close look at all the habitable zones it contains, we won't be able to use this method to establish a solid percentage for the likelihood of life in a habitable zone. We may be able to get there another way, though. Currently, scientists are looking at the atmospheres of planets in other solar systems. They're looking at these atmospheres for what are called biomarkers, or signs of life, because you don't have to go to a planet to see whether it has life, and we may be able to detect life at a distance just by looking at the light coming from their atmospheres. They've already found some interesting candidates for planets that may have life. They're still disputed, but we may eventually get convincing evidence for life on them. And if we do, we may be able to do a survey of the planets and other star systems and derive an estimate of how common life is that way.
In previous episodes, like the ones about life on Mars, you've pointed out that even if there is life there, it didn't have to start there. It might have come from Earth and traveled to Mars on meteorites that got knocked off of Earth's surface, the same way we have meteorites here on Earth that came from Mars. Does that affect the chances of life in any way?
I've seen some people argue that it would. In some discussions of the Drake equation, I've seen people say that we need to find life on other bodies in our solar system and show that the life arose there independently of life on Earth. But I think that's nonsense. To see why, let's define a couple of terms. The first term is abiogenesis. In Greek, a means not, bios means life, and genesis means beginning. So abiogenesis means beginning from non-life. In other words, the origin of life from non-living matter. The second term is panspermia. In Greek, pan means all, and sperma means seed, which in this case refers to the seeds of life. So from its roots, panspermia would mean that the seeds of life are everywhere in the universe. But it's come to mean the idea that life may travel from one place in the universe to another. And by the way, we'll have a future episode that's all about panspermia. The idea that we need independent origins of life in the solar system to use as estimates in the Drake equation confuses these two concepts. Abiogenesis may have just happened once, but that's irrelevant if panspermia is true and life migrates from one planet to another. For example, suppose that abiogenesis, or life emerging from non-living matter, only happened on a single planet in the universe, but then it migrated to other habitable planets. Well, if it took root in these other places, then it could grow and develop into later species, and some of those might eventually develop into civilizations we could detect. It just doesn't matter how often abiogenesis occurs if panspermia occurs too. What independent development of life in our solar system might do is let you estimate how common abiogenesis is, but it wouldn't tell you anything about how common life is unless you can show that panspermia doesn't happen, which is looking increasingly unlikely as we have organisms here on Earth that could survive the harsh environment of space. These organisms can exist in extreme conditions, and so they're known as extremophiles. So panspermia is looking plausible, in which case life can originate through abiogenesis in one habitable zone and then migrate to other habitable zones where it can grow and develop into other life forms.
In the absence of a direct measurement of how common life is, either here in the solar system or in other star systems, are there any other approaches that might let us estimate how common life is?
One thing that people have pointed to is how early life emerged on Earth. The scientific evidence that we have suggests that the Earth initially formed about 4.54 billion years ago, and we have evidence for life existing on Earth 4.1 billion years ago. So that's just 440 million years after formation, which is an incredibly short amount of time. This rapid emergence of life suggests one of two things happened. Either abiogenesis occurs very easily, so that life arose from non-living matter very quickly after the surface of the Earth became habitable, or panspermia happens, in which case the seeds of life arrived on Earth very quickly after its surface became habitable. Either way, we had life very quickly on Earth, and if it came about quickly here, we have no basis for assuming that it would take longer elsewhere in the universe.
Then where does all this leave us for a revised estimate for the life factor in the Drake equation?
I don't think we have a strong basis for challenging the original 1961 estimate, which was 100%. But I'm not comfortable leaving this one alone. My suspicion is that 100% is too high. So what other value might we pick? Well, here we have a binary choice between life emerging on a habitable planet and it not emerging, and we don't really know which is more likely. Well, if you have no data about a binary yes-no choice, like whether a coin will land heads or tails, then you assign each possibility 50%. So we could go with 50%. But I think the rapid emergence of life on Earth counts for something. So I'm going to split the difference between these two estimates. The average between 100% and 50% is 75%. So I'm going to provisionally assume that there's a 75% chance of life emerging on a habitable world.
Okay, so what about the percentage of planets that have life also having life forms that develop intelligence? What can we say here?
Back in 1961, they estimated the intelligence factor in the equation as 100%. In other words, if life exists on a planet, intelligent life is guaranteed to develop eventually. One argument for this is the increasing complexity of life over time. It apparently started with single-celled organisms, then it developed into multi-celled organisms, then simple plants and simple animals, and then more complex plants and complex animals, and finally us. So the argument goes that as life grows and diversifies, it increases in complexity. This is partly due to the fact that life's desire to survive makes it look for shortcuts. Originally, all life forms were what were known as autotrophs, that is, organisms that can make their own food from non-organic sources, like plants, which can make their food from sunlight, water, and chemicals like carbon dioxide. But then other life forms discovered that they don't have to make their own food. Instead, they can get their own food by eating other organisms. These organisms are known as heterotrophs. The first heterotrophs were those that ate autotrophs. Thus, in the animal world, many animals eat plants. We call these heterotrophs herbivores. But then other heterotrophs figured out that they could get their food not by eating autotrophs like plants, but by eating other heterotrophs like herbivores. And we call these creatures carnivores. There are also hybrids like us that can eat both plants and animals, so we're called omnivores. The problem that carnivores and omnivores have is that herbivores don't just sit there like plants. They can move around, they have some rudimentary level of intelligence, and they can run away and fight back. So carnivores need to be smarter than their prey. This sets up a scenario that will select for intelligence, as there's an arms race between herbivores and carnivores. As part of that arms race, the carnivores need to develop ways to defeat herbivore defenses. Those weapons may include things like strong claws and sharp teeth, but another potential weapon is intelligence. And so the competition to get food will eventually push some meat-eating life forms towards the development of progressively greater intelligence. Thus, once life emerges, it sets off a process that will lead to greater complexity and eventually to intelligence.
How have critics of this line of reasoning responded?
Well, some have argued that instead of the chance of intelligence emerging being 100%, something like the reverse should be true. These skeptics argue that out of the billions of species that have existed on Earth, only one of them, us, has become intelligent. So the chances of intelligence arising should be close to zero.
What do you make of this argument?
I think that whether or not its conclusion is true, that a planet developing intelligence is rare, that the argument is mistaken for several reasons. First, even if you assume that humans are the only intelligent species in Earth's history, doing a direct comparison with the number of species that have existed is a mistake. If you think about the history of life, you're not going to have intelligence as soon as the first microbe appears. Intelligence requires things like complex brains to host it. And so you're going to have a long series of non-intelligent creatures leading up to those with brains sophisticated enough to host intelligence. The existence of intelligence thus presupposes a large number of non-intelligent creatures first. So just saying, look at the number of other species that have existed compared to us is a mistake. Second, we don't actually know that we're the first intelligent species or even the first technologically sophisticated species in the history of Earth. It's possible that there was a prior race of intelligent technology users before us, but they all went extinct and all trace of them has been lost. This is a possibility that is known in science as the Silurian hypothesis. The name comes from the Silurians from Doctor Who. They were a race of intelligent humanoids back in dinosaur days who saw a disaster coming and went into hibernation. While the Silurian hypothesis is considered a long shot in real-world science, it isn't easy to rule out in principle, as we'll see in a future episode looking at the Silurian hypothesis. So the idea that humans are the first intelligent species may be wrong for this reason. Third, depending on how you define intelligence, we're simply not the first intelligent species in Earth's history. We may be the first with human-level intelligence, which could be the kind that you need to produce radio technology, but we're not the first tool users. And tools of any kind are a form of technology. Judging by tool use, there have been multiple species that have intelligence. They include not only us, but our near-human relatives and ancestors, like the Neanderthals and others, going back to Homo habilis. They also include the other primates, like chimpanzees and gorillas. They include elephants, they include dolphins, they include sea otters, they include certain birds, like crows and ravens. They include octopuses, and yes, octopuses is the correct English plural of octopus, and there are others yet. So we've actually had multiple instances of tool using intelligence develop on Earth. And once you're a tool user, you're within spitting distance of complex tools that could let you broadcast radio waves. I thus think that if humans vanished and opened up our ecological niche to some other species, that within a few million years, you might have another species fill it if God so willed. Of course, some species would be more likely than others. Since dolphins and octopuses live in the water, they're not good candidates for developing electronics because you can't even master fire and smelt metals underwater. Also, dolphins don't have the fine manipulators like our hands, so they can't build the kind of detailed tools we can. Octopuses do have the fine manipulators, but they live underwater, so they're not as promising for radio technology. Our most promising replacement species would likely come from the primate family, since primates both live on land and have fine manipulators in the form of hands with fingers. which is likely why God caused us to emerge out of the primate family ourselves. But if you set aside the question of technology, which is separate from the intelligence variable in the Drake equation, I think that we actually have multiple instances of significant intelligence developing here on our single planet. And so I think the chances of intelligent life developing on a planet with life is actually high, given enough time. I think that there is pressure created towards increase in intelligence once the heterotrophs start eating the autotrophs, and then carnivores and omnivores start eating the herbivores.
Do you then agree that we ought to set the intelligence variable in the Drake equation at 100%?
No, because there's another factor that we haven't focused on yet, and that's the time it takes for intelligence to develop. You'll notice that I said I think the odds of intelligence developing are high given enough time. Well, it takes time to develop a sophisticated brain. Earth is about 4.5 billion years old, and as far as we know, life first appeared on Earth 4.1 billion years ago. But all that life was single-celled. The first multi-celled organisms didn't appear, so far as we've discovered, until around 2.1 billion years ago. And the first animals didn't appear until around 575 million years ago, with the first carnivores appearing perhaps 500 million or half a billion years ago. Well, if Earth is about 4.5 billion years old and carnivores didn't appear until half a billion years ago, then you may need 4 billion years to get to the stage where there will be selection pressure put on organisms to develop intelligence. Once you get to that carnivore stage, intelligence might develop quickly, and I would have no problem with the idea that there were, for example, dinosaurs that used simple tools, the way some modern animals do. In fact, we have some rather startling evidence for dinosaur intelligence. One of the things that paleontologists do is look at an animal's encephalization quotient, which is the ratio of the size of its brain to the size of its body. It's not a perfect guide to how intelligent the creature was, but it's a useful measurement. Well, it turns out that the apex predator of the Cretaceous era, the carnivore we know as Tyrannosaurus rex, had an encephalization quotient comparable to that of a chimpanzee. T-Rexes have an encephalization quotient of 2.0 to 2.4, while chimpanzees have one of 2.2 to 2.5. T-Rexes also hunted in packs, just like wolves do. So imagine, as we will in a future episode, being hunted by a pack of T-Rexes as smart as chimpanzees. Scary. In any event, it may take 4 billion years to go from the appearance of life to having significant intelligence. And that means that a planet with life would need to remain hospitable to life for that long. But many planets don't fit that model. Many stars burn out in just a few million years. Other planets may be sterilized by supernovas. Others might get clobbered by asteroids way worse than what ended the dinosaurs. So while I do think that life likely develops towards intelligence, I don't think that you can count on a planet being stable long enough for that to happen. And I thus think that we need to set the intelligence variable at something less than 100%.
Then what value do you want to give it?
In the absence of more data, I think we have to fall back on basic probability principles. Here on Earth, we've had multiple species develop that have tool using intelligence, but Earth is very stable and has remained habitable for 4.6 billion years. So I think that tool using intelligence is likely inevitable given sufficient length of habitability. Unfortunately, in researching this episode, I wasn't able to get a current estimate of how many habitable worlds would remain so for several billion years. An astronomer might be able to provide a better estimate of that, but I can't at present. So I'm going to fall back on the 50-50 default for I just don't know, and assume that the chance of intelligence emerging is at 50%.
Then that brings us to the technology variable. What do you think the chance is of a planet with intelligence having technology develop that we could detect?
Well, back in 1961, they estimated that 10 to 20% of intelligent species would develop radio communications. This was because some intelligent species, like dolphins, which they talked about, wouldn't really be interested or have the ability to do that, since dolphins live underwater, making building electronics hard. and since they lacked fine manipulators like the hands that we use to build electronics.
And what do you make of this argument?
Well, I think that they're certainly right that not every intelligent species will develop radio technology. We've had many species with tool-using intelligence develop on Earth, but setting aside the Silurian hypothesis, humans are the only ones with the right combination of intelligence, circumstances, and abilities to do it. However, the question isn't what fraction of intelligent species will develop radio technology. It's whether at least one species with radio technology will develop on a planet. You may have a bunch of tool-using species on a planet, only one of which develops radio, which appears to be exactly the situation we have on Earth. There's also another problem with this argument, which is that it focuses on the use of radio wave technology, which includes both what we call radio and also television, since television signals are transmitted by radio waves. The reason they were focused on this is that they were interested in finding someone they could talk with. And so they were primarily focused on intelligent beings that developed the ability to communicate with other star systems by radio waves. They acknowledged that not all such species might be interested in communicating with others, but even so, we still might be able to detect them the same way that creatures in nearby star systems could detect the radio and television signals that Earth was broadcasting for decades before Frank Drake sent the Arecibo message to another star system. Still, radio is not the only technology that we might be able to detect at a distance. For example, even if we couldn't detect radio waves coming from a star system, we might be able to detect laser light coming from it if they use lasers to communicate or to power ships with light sails. Also, if the aliens had built megastructures around their stars, like a Dyson sphere or Dyson swarms to collect its sunlight, we may be able to detect those technologies as well by looking at the light from the star. And by the way, we discussed such possibilities in episode 348 on the Kardashev scale. So we need to be thinking a bit more broadly than they were in 1961. Radio communications are one technology that we might detect, but we need to be thinking in terms of any technosignatures that we might find.
Then what value would you assign to the technology factor in the Drake equation?
It's hard to say. I've read in Frank Drake's account of the 1961 meeting some of the things that they discussed about the chance of a species developing radio. And the other technosignatures that we might detect all involve things more complicated than radio. So we can treat developing radio as a first step in the world of detectable technology. But Drake really doesn't go into how they arrived specifically at 10 to 20% as their estimate. It looks like this may have been primarily a guess on their part. And so I'm going to do my own reasoning. Any planet that develops intelligent life has to be quite stable in terms of its habitability, like Earth was for the first 4 billion years before carnivores developed. That's not to say that you can't have planetary disasters like dinosaur-killing asteroids that set things back, but setbacks are just that, setbacks. They don't end the process of developing intelligence. And here on Earth, we've developed multiple species with tool-using intelligence. Given that abundance of tool users and the competition that drives greater intelligence forward, I think it likely that at least one tool-using species will develop radio signals and thus detectable technosignatures on a basically stable planet, unless there's some major factor that prevents this, like the entire surface being covered by oceans that effectively stop metallurgy and electronics from being developed. And I would note that you could still develop electronics underwater, but it would be much, much harder than if you have dry land. So I'm going to put the chance of some species of tool makers on a planet developing technosignatures higher than the 1961 estimate. Assuming that a planet is basically stable, which the emergence of intelligent life has already demonstrated that it is, I put it at 100%, except for the fact that some planets might be covered with oceans and some previously stable planets might have a life-ending disaster. So I'm going to bring it down to 75%.
That leaves us with the last factor in the Drake equation. You called this the lifespan of how long a civilization continues to communicate. What value should this be given?
Here's where I'm going to part company in a big way with the 1961 estimates. Back then, they estimated that a civilization that developed radio would likely remain detectable for 1,000 to 100 million years, though they acknowledged that some civilizations may do this for less than 1,000 years. But I think they didn't place enough emphasis on the lower end of the range, and for several reasons. First, there's a significant chance that any radio-using civilization will destroy itself in short order, because any species that have the intelligence for technology is almost certainly a carnivore or an omnivore, which means they have a history of violent conflict. Well, within decades of developing radio, we developed the atom bomb. And if we got into a serious enough nuclear conflict, it hypothetically could kill off the human race. We also could kill ourselves through the development of biological weapons, which we also began custom building within a few decades of radio. In fact, the possible self-destruction of a species is one of the proposed solutions to the Fermi paradox. In other words, we don't see evidence of aliens because their conflict impulse from their carnivore or omnivore heritage pushes them to kill themselves quickly once they get to this stage of technological development. However, this is not the only problem with the idea that such civilizations might be detectable only for short periods. Even here on Earth, we emit far fewer electromagnetic transmissions than we used to. For example, we no longer broadcast television signals out into space in the same way. Now we have cable television and internet lines, so a civilization might be detectable by its radio emissions only in the early stages after they get radio. And then, as they get more sophisticated, they develop more focused communications technologies that don't broadcast electromagnetic signals all over the sky. In which case, you'd see a brief flowering of the signals that would vanish within a few decades. And if the species is more paranoid than we are, they might even decide to stop using broadcasting precisely to avoid being detected by aliens. Of course, they might then go on to develop really high tech that we could perceive in another way, like building a Dyson swarm around their star. But they might not produce that techno-signature for 500,000 years or something, and there would be a long dark between when they were briefly detectable with radio waves and when they became detectable again through large-scale engineering. There's more that I could say about all this, but I think the bottom line is that the range of best guess values in 1961 was too narrow. We could have offed ourselves within 50 years of getting radio. So instead of 1,000 to 100 million years, I'm going to set the lifespan value at 50 to 100 million years.
Then what figures do we come up with when we use the revised numbers you've provided for the Drake equation?
Well, we have two factors in this equation that are ranges. We estimated that the number of habitable places per star system with planets would be 1 to 5, and we estimated that the lifespan during which a technological civilization would be detectable would be between 50 and 100 million years. So we'll run the equation twice, first assuming the minimum values and second assuming the maximum values. If we pick the minimum numbers, then the number of detectable civilizations in the Milky Way would come out to be 211, which is a very small number, given that there are thought to be between 100 and 400 billion stars in the galaxy. We'll average those numbers and assume there are 250 billion stars. So if there are only 211 detectable civilizations, that would be one detectable civilization per billion stars. And if we pick the maximum values, then the number of detectable civilizations in the Milky Way would come out to be 2,109,375,000. Assuming that there are 250 billion stars in the galaxy, that would be one detectable civilization for every 100 stars. So this is an extraordinarily wide range. Given our present state of knowledge, we can't use the Drake equation to make confident predictions about the actual number of such civilizations. My own suspicion is that the actual number is toward the lower end of the scale, but we really need to firm things up with a bunch more data. Still, it's a useful thought exercise to see what the possibilities are and to think about what kinds of things we need to know to get a good estimate and thus what needs to be researched. It's also useful as a cautionary tale because by thinking it through, we've seen how widely divergent the estimates can be. It all depends on what factors you put into the equation. So when you hear mediocritarians saying that civilizations should be common in the galaxy, it's because of the variables they're putting in, many of which are just guesses. And when you hear rare earthers declaring that civilization should be rare or even non-existent elsewhere in the galaxy, it's also because of the variables they're putting in, again, with many of them being just guesses. I think the honest answer for how many detectable civilizations are there at present in the galaxy is nobody honestly knows.
And remember that the Drake equation is focused on how many detectable civilizations there are, not how many planets there are with life or even with intelligent life.
That's correct. There could be lots of planets with life, very few of which have intelligent life, or there could be lots of planets with intelligent life, very few of which are detectable because they're not throwing off technosignatures that we know how to find. The Drake equation is focused specifically on how many technological civilizations we could detect at present.
So far in today's episode, we've assumed the Drake equation and then discussed the numbers that should be plugged into its variables. But it's been 64 years since the equation was developed. Are there any fundamental changes that should be made to the formula itself?
This is a very interesting question, and I think that the answer is yes. The factors it contains are good, but I think we should add some. Sometimes rare earthers propose add in new factors to the equation, like whether a star is close to the galactic core, whether a system has a Jupiter-sized planet in the right position to deflect asteroids from the habitable planets, and whether habitable planets have the right axial tilt to give them seasons and things like that. But I think that we shouldn't add those to the equation because what they're really doing by these added factors is just driving down the number of habitable places there are. In other words, what they're doing is just modifying the habitability number, saying it should be lower than in other estimates. And that's fine. If you want to argue the habitability number should be low, great. Make your arguments about galactic cores and axial tilts and Jupiter-sized planets in the right places. Those are all factors that will help you do the calculation of the habitability number, but we don't need to add them as new terms into the equation. We just need to fold them into the habitability number. On the other hand, I do think that there are two additional factors that merit further consideration. One of them is what some have called the reappearance factor. That is the number of times a detectable civilization emerges on a planet where it has already happened. This would be one way of accounting for the long dark period that may exist between when a civilization is first experimenting with radio waves and can be detected, before it goes into the long dark the way we're doing now, and when it develops something like a Dyson swarm that would make it detectable again. A reappearance factor also would be a way of handling things like the Silurian hypothesis, where one detectable civilization appears on a planet but then dies out and another one develops. And these might be civilizations even with the same species. Like we might have been detectable from nearby star systems when we first invented radio, but then if we had gotten into a big nuclear war in the mid-20th century that knocked us back to the Stone Age, we'd lose our detectability. And if that war didn't kill us altogether, well, then within a few centuries, we might have built back up again to the level of being detectable. So I think that it could be reasonable to add a reappearance factor or to some versions of the equation. Even more important is what I'll call spread. That is, how many other star systems has a civilization spread to? If it's only in its home system, a civilization would have a spread of 1. If it's colonized another solar system, its spread would be 2. If it's colonized 10 systems, its spread would be 10, and so forth. Back in 1961, the attendees at the conference assumed that detectable civilizations didn't spread between star systems, so they assumed that the spread of each civilization was 1. They all just occupied one star system. But today, many scientists recognize that faster-than-light travel may be possible, and even without faster-than-light travel, an advanced civilization could get between stars using slower-than-light means. It's also been estimated, for example, that such a civilization could explore and colonize the entire galaxy in 1 million years or so. So if some civilizations last for 100 million years, like they estimated in 1961, they could easily spread across significant chunks of the galaxy. In its current form, what the Drake equation really does is tell us the number of origin points for detectable civilizations. But if we're interested in detecting extraterrestrial intelligence itself, then what we need to know is how many total stars are associated with technosignatures that we could find. So you also need to look at more than just the origin points and consider how far a civilization has spread since it originated.
Is there anything else you'd like to say before we go?
Yeah, I mentioned that two of the factors in the Drake equation that we might be able eventually to get estimates on are the number of planets with life and the number of planets with detectable technology. We could measure the first by looking for biosignatures around other stars, and we could measure the second by looking for technosignatures around other stars. Well, scientists have been trying to do both of those things, and they've turned up some possible hits. In 2025, some astronomers announced that they may have found biosignatures in the atmosphere of an exoplanet named K2-18b, which is 124 light years away. And in 2023, another team announced that they had used AI to look through radio signals from a group of 820 stars to see if they could find any ones that looked artificial. And they found 8 candidates that looked like they might be artificial. So we have promising news on both the biosignatures and the technosignature fronts. Now, that doesn't prove that what we found is what we're looking for. When things like this are announced, they are always challenged, they always receive pushback, and often alternative explanations are found. But the search for life and the search for intelligence still look promising.
So, Jimmy, what's your bottom line here?
The Drake equation is a useful tool. Given our present state of knowledge, we can't use it to make specific predictions. The factors it includes involve too many unknowns for that. And so people can come up with wildly different estimates, with mediocritarians estimating that there are a large number of detectable civilizations and rare earthers estimating that there should be few or none. But the Drake equation is a useful guide in thinking through the problem of detecting extraterrestrial civilizations. The debate over the Drake equation and what values it should be assigned is helpful, since science advances by testing alternative ideas against each other. The equation serves as a guide to figuring out what we need to know, and this can help guide further research. It's also possible that before too long, we might even detect clear technosignatures coming from off Earth.
And what further resources can we offer?
We'll have a link to Frank Drake's book, Is Anyone Out There? Also information about the Drake equation. We'll have a link to the SETI Institute. Also Frank Drake's speech where he described the origin of the equation, the 2023 findings on star formation, Bach's Brandenburg Concerto No. 2, and Johnny B. Good, if you want to hear them both in their full glory. Also, information about dinosaur intelligence that focuses not just on the encephalization quotient, but also the number of neurons in their brains. Information on biosignatures, technosignatures, the possible biosignatures that were detected, and the original paper on the technosignatures that may have been detected.
Very good. So now we turn to our mysterious feedback brought to us by our feedback coordinator, Rob Leonardi. This feedback comes from our recent episode on the mystery of the year. And John writes on Facebook, I want to know why we shouldn't refer to the time before Christ as BC and why people use BCE, before Common Era, instead. It seems like a pushing out of God to do that.
Well, I certainly understand the sentiment. The alternative, and it'll take a second for this to become clear, but the alternative to BC, its opposite is AD. And so if you replace BCE with before the Common Era, then the replacement for AD becomes Common Era. And the term Common Era actually goes back to the 1600s. It was originally used by Johannes Kepler. And it was not used for modern purposes. It was just like, this is what the common people use as their era. But then so it'd kind of be like saying, oh, this is the year 2025 in the Common Reckoning. And so it originally was not an attempt to exclude Jesus. But in the 1800s, some Jewish scholars began using it as a replacement to say, okay, we're kind of together now. Christians and Jews together. We have this common era, and then there's this period before the common era. And it was really the same thing as BC and AD, but it was felt to be more inclusive. And that's something that I certainly understand. There's only a few million Jews in the world today, and there's, several billion Christians. And so I understand Jewish individuals like kind of wanting to integrate and feel accepted as part of a broader community, and that's all great. And I can understand why they might not feel comfortable, if they're not convinced of Christianity, why they might not be comfortable thinking of Jesus as our Lord, and if they don't think of him as the Christ, saying before Christ, if that's not who they think he is. So I can kind of understand the impulse to go to this is a common era that we Jews and Christians, even though we have our differences, we're together now. And so this is a nice way of including everybody. And then with greater secularization in the 20th century, other people wanted to be included too, and because no one's going to displace the AD, BC years themselves. We're not going to say, oh, we're starting over, it's year one. That's not going to happen in the foreseeable future. So this effort using BCE and CE is an effort to be more inclusive, but personally, I feel it's unnecessary because it's not really changing anything, and people who are so fragile, they need affirmation every time they say a year with its associated epoch, need to not be that fragile. And I even know Jewish individuals who've said they don't like the BCE CE thing. This is the system the Christians came up with. We Jews have our own Anno Mundi thing, and we just use whichever one's convenient. And so I understand how this system developed. Personally, I don't think it's necessary, and personally, I don't use it unless I'm required to by the venue I'm publishing in.
So that's it for our feedback, and now it's time to hear from you. What are your theories about the Drake equation and the possibilities it raises? You can let us know by visiting sqpn.com or the Jimmy Akin's Mysterious World Facebook page, sending us an email to feedback@mysterious.fm, sending a tweet to @MYS_world, visiting the StarQuest Discord community at sqpn.com/discord, or by calling our mysterious feedback line at 619-738-4515. That's 619-738-4515.
And I want to say a special word of thanks to Oasis Studio 7 for the video and animation work on this episode. We recently passed our first goal of 100,000 subscribers on YouTube. So please help us get to our next goal of 200,000. You can go to youtube.com/Jimmy Akin to find the video version of the podcast and all the other videos I put out. While you're there, be sure and like, comment, subscribe, and hit the bell notification so YouTube will actually tell you when I have a new video.
Very good. So, Jimmy, what's our next episode going to be about?
Next week, we're going to be looking at some recent congressional hearings about the JFK assassination and how the government and its agencies responded to it. A group of eyewitnesses made some serious charges in these hearings, and we'll be hearing what they had to say, including from a doctor who treated President Kennedy himself immediately after the assassination.
Interesting. Be sure to check out the Mysterious World bookstore at mysteriousworldstore.com for links to all the books and videos that Jimmy mentions in the show. Get your very own Mysterious World t-shirt, mug, and more in our merchandise shop at sqpn.com/merch. You'll find links to Jimmy's resources from our discussion on our show notes at mysterious.fm/372. And remember, to help us continue to produce the podcast, please visit sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you in part by Rosary Army, featuring award-winning Catholic podcasts, rosary resources, videos, and the School of Mary online community, prayer, and learning platform. Learn how to make them, pray them, and give them away while growing in your faith at rosaryarmy.com and schoolofmary.com. Until next time, Jimmy Akin, thank you for exploring with us our mysterious world.
Thanks, Tom.
And once again, I'm Dom Bettinelli. Thank you for listening to Jimmy Akin's Mysterious World on StarQuest.